In this video, we're going to be looking at the ionization process that occurs in bases. This is a little bit strange because when most people think of a base, they think of an ionic compound like NaOH because it contains the hydroxide polyatomic ion, and therefore you can identify it as a base. These are not the bases we're talking about, as these bases, since they're ionic compounds, would undergo dissociation in water. Rather, we're going to be looking at NH3, ammonia, and other compounds that contain nitrogen and that use this nitrogen in order to undergo an ionization that is similar but distinct from acids. Now, if we analyze the polarity of ammonia, we know that nitrogen has a higher electronegativity than hydrogen does, and nitrogen also has a lone pair, whereas hydrogen does not. Therefore, because of the electronegativity difference and because of the movement of electrons in all of the bonds in ammonia to nitrogen, nitrogen is going to be the negative side of this molecule, and each of the hydrogens is going to have a positive pole. Now, what this means is that the lone pair on nitrogen can attract to the positively charged hydrogen that we find on water. And the turning of a lone pair into a bond, as we saw in acid ionization, is exactly the same mechanism that happens, only in this case the lone pair does not come from water, it comes from nitrogen's lone pair here. So again, the negative pole on the nitrogen side of ammonia can attract to the positive pole of the hydrogen on water, and nitrogen's lone pair is going to be converted into a bond the same way that we saw in acid ionization. Now again, we run into the same problem. We're trying to make a bond with a hydrogen that already has a bond, only this time the bond that we're going to break is in water rather than in the acid compound. So because hydrogen cannot make two bonds, the existing bond that exists between hydrogen and oxygen in water is going to break. But since we can't create or destroy electrons, we can take those electrons from the bond and move them to oxygen, where they would then exist as a lone pair. So what we see in base ionization here is that rather than water removing a hydrogen from acid, NH3 is going to use its dipole to remove a hydrogen from water instead. Now, if we keep track of electron movement here, we see that this bond in water has broken, and the electrons are going to move to oxygen, which means that we can see from this arrow we've drawn that oxygen has gained electrons. And because the oxygen in water has gained electrons, it is going to have a fully negative charge, which is how we end up with OH-. So we can see that even though NH3 does not contain OH- like ionic bases do, we see that when we put NH3 into water, because it pulls one of the hydrogens off of water, it produces OH-, even if it doesn't contain OH- initially. Now, whenever we create a negative charge, we also need to create a positive charge somewhere, and we can see that on NH3. Because its lone pair are moving away from nitrogen here, we can say that nitrogen has lost electrons because this lone pair that used to belong only to nitrogen is now this bond. So this bond used to be the lone pair. So because these electrons are now shared between hydrogen and nitrogen, instead of only belonging to nitrogen, we say that nitrogen has lost electrons, and therefore the nitrogen is going to have a positive charge, which is exactly what we see in its structure like this. If we put this reaction into writing, we say that the nitrogen on NH3 is going to take an H+ away from water and therefore give us NH4+ when it is added to water, and we can tell that this compound is acting as a base because we produce OH minus, the hydroxide ion, as a result of this reaction. To compare acid and base reactions in a more general term so that we can see the difference between the two, remember in acids that water is actually going to be taking the H plus away from acids, or a different way that we can look at it is that acids are going to lose H plus. In fact, that's the literal definition of this acid. So water removes H plus from the acid, and because water is taking the H plus away from the acid, it is now going to produce this weird ion here, which is a water molecule with 3 hydrogens instead. This ion is what we call the hydronium ion. In terms of the name, usually when an ion ends in ium, it indicates that there is some sort of positive charge, and the fact that this is hydronium indicates that this is a positive charge that exists on something that used to be water. Conversely, in a base ionization here, it is the job of the base, again, usually something that is going to have a nitrogen atom with its lone pair. The base is going to take an H plus away from water like this, and therefore water is going to be losing its H plus molecule. And when bases remove an H plus from water, all that is left of that water molecule is OH minus, the hydroxide ion, as we have seen before in ionic bases like NaOH. That concludes our series of videos on dissociation and acid and base ionization. To confirm and reinforce your knowledge, there are plenty of additional practice problems below. This section covers base ionizations, and the section before would cover acid ionizations. Use these practice problems to actually draw the reaction that happens, show how an organic base will take a hydrogen from water, or show how organic acids will lose hydrogen in water, and write out what the reaction is and identify what the products are based on the general ionization reactions that you are given here.